The Untold Story of Artificial Intelligence, from 1950 to the present. The history of artificial intelligence, AI, is often recounted as a linear progression punctuated by moments of genius and sudden revolutionary breakthroughs. This popular narrative typically centers on the Dartmouth Conference, 1956, the rise and fall of symbolic AI, the two AI winters, and the recent seemingly abrupt emergence of deep learning and large language models, LLMs. However, the true story, the untold story, is far more complex. A narrative of persistent, often ignored figures, crucial incremental steps, and the surprising convergence of hardware, data, and algorithmic vision that defied decades of skepticism. This document explores the hidden currents of AI history from 1950 to the present, focusing on the lesser-known people, the overlooked technological enablers, and the critical lessons learned from the field's most significant paradoxes. Part 1. The Dawn and the Silent Enablers, 1950s-1970s. The foundational era of AI is defined by the work of figures like Alan Turing and John McCarthy. Yet the story of this period is incomplete without acknowledging the silent enablers whose work made complex AI programming possible, and the pioneering systems that demonstrated early capability but failed to achieve real-world adoption. The architect of feasibility, Grace Hopper. While not a direct AI researcher, Grace Hopper's contribution was a crucial, overlooked prerequisite for all subsequent AI development. Her pioneering work in the early 1950s on automatic programming led to the creation of the first compiler, Flow-matic. This innovation allowed programmers to write code in something resembling English rather than low-level machine code, dramatically simplifying the process of creating complex software. Without this shift to higher-level programming languages, the intricate algorithms required for early AI systems like the logic theorist and general problem solver would have been prohibitively difficult to design and implement, effectively stalling the field before it could begin. Hopper's work was the foundation upon which the entire edifice of AI software was built. The mechanical marvels and the proof of concept, the 1960s and 1970s saw the creation of systems that proved the technical feasibility of intelligent machines, even as the field struggled with the limitations of the hardware. System year, approx. Significance, technical, untold story, contextual. Shaky the Robot, late 1960s first mobile robot to reason about its actions. Integrated perception, world modeling and planning, strips. Its slow, deliberate movements and large size masked the sophistication of the underlying software, which laid the groundwork for modern autonomous systems and robotics. MYCIN 1970s expert system for diagnosing blood diseases and recommending antibiotic treatments. Sometimes outperformed human doctors, cells. The system's technical success was a paradox, as it was never adopted in clinical practice. The failure highlighted the gap between laboratory success and real-world integration, a recurring theme in AI history. Part 2. The Winter and the Paradox, 1970s-2000s. The 1970s and late 1980s were marked by periods of reduced funding and skepticism, known as the AI winters. During these times, two distinct groups of researchers kept the field alive: those who doubled down on the dominant symbolic approach, and those who quietly persisted with the then unfashionable connectionist neural network paradigm. The symbolic standard-bearer, Elaine Riches. The symbolic AI approach, which sought to represent human knowledge explicitly through rules and logic, reached its peak. A key figure was Elaine Rich. Her influential textbook, Artificial Intelligence, became the standard reference for a generation of researchers, cementing the dominance of the symbolic approach during the 1980s. Rich's work on knowledge representation and expert systems was central to the field's focus at the time, demonstrating the power of logic-based reasoning. Her persistence helped sustain the field's academic credibility, even as funding for expert systems dried up. The MYCIN paradox: technical success versus real-world failure. The story of MYCIN is perhaps the most instructive untold lesson of the AI winters. Despite its proven diagnostic accuracy, the system failed to integrate into hospitals for reasons that had nothing to do with its intelligence. The core issues were integration. It was a standalone system, incompatible with existing hospital workflows. Liability. There was no legal framework for who was responsible if the AI made a mistake. Brittleness. It lacked common sense and could only function within its narrow domain, failing catastrophically outside it. This paradox taught the field a critical lesson. AI's ultimate success is not just an algorithmic problem. It is a problem of human-computer interaction, organizational change, and societal trust. The connectionist persistence. The unfashionable few. While symbolic AI enjoyed the spotlight, a small group of researchers, most notably Geoffrey Hinton, quietly continued to pursue the neural network approach. For decades, this work was dismissed as a dead end, especially after the limitations of the perceptron were publicized. Hinton and his colleagues persisted with the backpropagation algorithm, which was the key to training deeper networks. Their commitment to this unorthodox idea during the long winter years was the hidden fuse that would eventually ignite the modern AI explosion. Part 3. The Perfect Storm, 2000s-2010s. The AI boom of the 2010s was not a sudden miracle, but the result of the simultaneous and largely uncoordinated convergence of three distinct visions, each pursued by a visionary who defied conventional wisdom. Visionary contribution, the unorthodox vision. Why it was essential, Geoffrey Hinton. The algorithm. Persisting with deep neural networks and backpropagation when the field favored symbolic AI and support vector machines, SVMs, provided the scalable, nonlinear function approximator capable of learning complex patterns. Jensen Huang, the hardware, recognizing that NVIDIA GPUs, designed for parallel graphics processing, were the ideal architecture for the parallel matrix calculations of neural networks, provided the massive, affordable computational power needed to train models with millions of parameters. Fei-Fei Li, the data, creating ImageNet, 14 million labeled images, a dataset considered ludicrously large by her peers, provided the necessary fuel, data, for the deep learning algorithms to finally demonstrate superior performance in the 2012 ImageNet competition. The true untold story of the deep learning revolution is that it required the simultaneous maturation and convergence of these three elements: algorithm, hardware, and data, a perfect storm that caught almost everyone by surprise. Part 4. The Silent Revolution, 2010s present. The final and perhaps most subtle, untold story is that of the transformer architecture and the rapid democratization of AI that followed. The 2017 paper, Attention is All You Need, which introduced the transformer, is often cited as a sudden, revolutionary moment. However, the key insight was an incremental leap built on existing work. The concept of attention was not new. It had been used in conjunction with recurrent neural networks, RNNs. The true revolution was the decision to dispense with recurrence and convolutions entirely and rely solely on the multi-head attention mechanism. This seemingly minor architectural change unlocked two massive capabilities. Massive parallelization. It allowed the entire input sequence, a sentence, a paragraph, to be processed simultaneously, drastically reducing training time. Long-range context. It allowed the model to maintain a strong connection between words far apart in a sequence, solving a fundamental problem of older architectures. This architectural shift, combined with the rise of open-source frameworks like TensorFlow and PyTorch, accelerated the field exponentially. The story of modern AI is not just about the technical breakthrough of the transformer, but the democratization of that technology, which allowed thousands of researchers and companies to build upon it, leading directly to the current era of generative AI and large language models. Conclusion. The persistence of the untold, the history of AI from 1950 to the present, is not a tale of inevitable progress, but a story of persistence, paradox, and convergence. The field was repeatedly saved by researchers like Grace Hopper, Elaine Rich, and Jeffrey Hinton, who pursued their visions despite the prevailing skepticism of their eras. The failures of early, technically successful systems like MYCIN taught the crucial lesson that AI is a socio-technical challenge, not a purely computational one. Ultimately, the untold story reveals that the current AI boom is not a magical event, but the culmination of over 70 years of incremental, often overlooked work.